Imagine standing at the rim of the Philippine Trench, if standing were even a thing you could do on a moving tectonic plate beneath several kilometers of ocean. The water above you still feels familiar at first. Light filters down in soft blue ribbons. Fish still look like fish, and gravity behaves itself. But then the sea floor tilts, and the world begins to fall away. This is not a gentle slope like a rolling hill. This is an underwater cliff system that drops so sharply it feels like the planet forgot to install a guardrail. As you descend, sunlight fades faster than your phone battery on a road trip, until eventually the concept of day and night just quietly resigns. Pressure, meanwhile, is doing push-ups. Every 10 meters down adds the weight of another atmosphere, and by the time you are sliding along the trench slope, the water above you is pressing with the enthusiasm of an entire mountain range. Down here, pressure is not an inconvenience. It is the landlord. Anything that lives along these slopes has signed a long-term lease agreeing not to pop, crack, implode, or panic. If humans tried to follow without protection, we would become a very brief cautionary tale. If this calm journey into what lives along the slopes of the Philippine Trench helps you relax tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this gentle science can reach more people who drift off to sleep with the deep ocean. The Philippine Trench itself stretches along the eastern edge of the Philippines, carved where tectonic plates collide in slow-motion violence. As the slopes are the trench's shoulders, not yet the deepest point, but already far beyond anything the surface world would recognize as normal. This is the realm where extremes start stacking on top of each other. Cold temperatures hover just above freezing. Food does not arrive on a schedule. There is no photosynthesis, no gentle warmth, no easy living. And yet, this is not a dead zone. It is a threshold, a place where the ocean begins showing off what life looks like when it stops caring about comfort. As we descend, the water grows darker, thicker, quieter. Sound behaves strangely here, muffled and distant, as if the ocean itself is holding its breath. The slope beneath us is uneven, scarred by geological activity that never really sleeps. Earthquakes ripple through this region from time to time, subtly reshaping the walls. Where gravity pulls loose sediments downhill in slow-motion avalanches, constantly rearranging the landscape. The trench slopes are not static scenery. They are alive in a geological sense, shifting and sliding over timescales that make calendars feel deeply optimistic. What makes this place so important is that it is not the deepest abyss yet. These slopes are a transition zone, a long descent from the familiar to the truly alien. Think of it as the ocean's backstage area, where life is changing costumes before stepping into the deepest, darkest spotlight. The conditions force organisms to adapt early, long before the seafloor drops away entirely. Here, evolution starts getting creative, quietly testing ideas that would seem ridiculous anywhere else. Food, for example, does not come from sunlight here. Nothing grows quickly. Nothing grows easily. Whatever energy exists arrives from above, drifting down in tiny fragments or sliding sideways along currents. The slopes catch and funnel this material, making them hotspots compared to the emptier depths below. It is not abundance, but it is opportunity. And in the deep sea, opportunity is everything. Life here survives not by speed or strength, but by patience, efficiency, and the ability to make a meal out of almost nothing. As we glide along the slope, it becomes clear that this is not just a passageway to somewhere else. It is a destination in its own right. The terrain offers ledges, cracks, overhangs, and sediment fields, each one a potential foothold for something stubborn enough to claim it. These slopes are the ocean's proving ground, or where life practices surviving before committing to the deepest extremes. If the deep sea were a marathon, the trench slopes would be the part where runners stop smiling and start questioning their life choices. And yet, life does not merely endure here. It settles in. It adapts. It builds ecosystems in slow motion, thriving in ways that feel almost disrespectful to the harshness of the environment. This opening plunge is our invitation into that world. A world where the rules are different, the margins for error are microscopic, and survival itself feels like a punchline to a joke the ocean has been telling for millions of years. If you could peel the ocean away like a blanket and look directly at the slopes of the Philippine Trench, you would not see a smooth, dramatic drop into darkness. You would see chaos. Beautiful, layered, geological chaos. These slopes are less like a single cliff and more like a vertical city built by earthquakes, gravity, and time, all working without blueprints and absolutely refusing to clean up after themselves. The trench slopes begin where the continental margin gives up pretending to be stable. The seafloor tilts downward, then breaks into a series of steep walls, angled shelves, fractured ridges, and sediment-covered ramps. Some sections plunge sharply, almost straight down. Others flatten briefly, forming terraces that look like nature paused mid-collapse. These terraces are not decorative. They exist because the Earth's crust here is under constant stress as tectonic plates collide and slide beneath one another. The slopes are shaped by this slow-motion wrestling match, and every tremor leaves its mark. While one of the most dramatic forces sculpting these slopes is underwater landslides. When sediments pile up on steep angles, gravity eventually wins the argument. Entire sections of the seafloor can slump downward, dragging mud, rocks, and debris along with them. These slides carve scars into the slope, exposing hard rock in some places while burying others under fresh layers of sediment. Imagine a mountain range where avalanches happen in total darkness and take decades to finish falling. That is the trench slope experience. Over time, these landslides create a patchwork landscape. Jagged rock faces rise like underwater cliffs, their surfaces rough and uneven. In between them lie gentler sediment plains, where fine particles settle and accumulate. Some areas are constantly disturbed, reshaped again and again by shifting material, while others remain relatively stable for thousands of years, becoming long-term real estate in an otherwise unpredictable neighborhood. The result is a vertical mosaic of habitats, stacked on top of one another, each defined by slope angle, surface texture, and exposure to currents. Currents play a quiet but powerful role here. As water moves along the trench slopes, it is guided by the terrain, accelerating through narrow channels and slowing over flatter ground. This movement determines where sediments settle and where they are swept away. Over time, currents carve subtle pathways along the slope, forming grooves and channels that further divide the landscape. These water movements also transport dissolved chemicals and organic particles, subtly influencing which areas become more favorable for life and which remain comparatively barren. The terraces are particularly important features. These step-like formations interrupt the descent, creating horizontal or gently sloped platforms along the trench wall. Some are wide enough to stretch for kilometers, while others are narrow ledges barely clinging to the slope. Terraces form when geological layers with different strengths erode at different rates, or when large landslides leave behind flattened remnants. They act as natural catchment zones, trapping sediments and materials that would otherwise slide into deeper waters. In a place where stability is rare, these terraces offer something precious: consistency. Jagged walls, on the other hand, are all about exposure. Where landslides or tectonic fractures have stripped away loose material, hard rock is left behind. These walls can be nearly vertical, or riddled with cracks and crevices formed by stress and chemical weathering. They are constantly bathed in moving water, making them very different environments from the calmer sediment fields below. The contrast between these surfaces creates sharp boundaries in the landscape, like switching from a rocky cliff face to a sandy slope in just a few meters. All of this complexity means that the trench slopes are not a single environment, but many layered ones. Depth changes quickly over short distances, so conditions can vary dramatically from one ledge to the next. Temperature, current strength, and sediment type can all shift within a vertical span smaller than a skyscraper. It is less like descending into a void and more like moving through stacked floors of a building, each one with its own layout and rules. This geographic diversity is what makes the slopes so important in the larger deep-sea system. Instead of a uniform abyss where everything is the same and nothing stands out, the trench slopes offer variety. They create niches, pockets, and gradients that allow different forms of life to settle in different places. The terrain itself becomes a sorting mechanism, determining who can live where and why. So when we imagine the Philippine Trench, it helps to stop thinking of it as a single dramatic plunge into nothingness. The slopes are not empty hallways leading to the abyss. They are a layered neighborhood, carved by gravity and time, full of geological personality. A place where the sea floor tells a story written in scars, shelves, and sharp angles, quietly shaping everything that dares to live upon it. Whereas when most people hear the word coral, their brain immediately pulls up images of tropical reefs glowing with colour, sunbeams slicing through turquoise water, and fish that look like they were designed by a committee of artists who refused to agree on a palette. The corals along the slopes of the Philippine Trench would like to formally decline that association. These corals live in complete darkness, at depths where sunlight is nothing more than a myth passed down by plankton legends. And yet they are very much coral, just stripped of the flashy marketing. These are cold water corals, and unlike their shallow water relatives, they do not rely on photosynthetic partners. No sunlight means no algae roommates paying rent with sugar. Instead, these corals survive the old-fashioned way, by eating. Tiny food particles drifting through the water, fragments of organic matter, microscopic organisms, and nutrient-rich debris are captured by delicate tentacles and pulled toward waiting mouths. It is slow, methodical feeding, more like sipping soup through a straw than chasing a meal. If efficiency were an Olympic sport, these corals would medal without ever moving. The slopes of the trench provide an ideal setting for this lifestyle. Positioned along ledges and angled surfaces, these corals take advantage of passing currents that deliver food like a conveyor belt. They orient themselves carefully, growing upward and outward to maximize exposure. Over time, individual coral polyps build skeletal structures made of calcium carbonate, stacking generation upon generation into branching forms that resemble pale underwater forests. Or, in the darkness, their skeletons appear white or faintly tinted, giving rise to the nickname ghost reefs, which sounds spooky but mostly reflects how little we see them. Growth here is not fast, not even a little. Some of these corals grow just millimeters per year, which means a colony the size of a dining table may be centuries old. These reefs are archives of deep-sea history, recording changes in ocean chemistry and currents within their layers. If trees have rings, these corals have memories, stored in stone-like frameworks built one patient polyp at a time. They are living proof that take it slow is not just advice, it is a viable survival strategy. The structure of these coral reefs transforms the trench slopes in subtle but powerful ways. By rising off the seafloor, they create three-dimensional habitat in an environment that might otherwise be relatively bare. Branches and crevices offer shelter, surfaces for attachment and protection from currents. Over time, entire communities form around these coral frameworks, using them as anchors in a world that otherwise tends to slide downhill. The coral becomes architecture, and the slope becomes a neighborhood, rather than just a descent. What makes this even more remarkable is how precise the corals must be about where they settle. Too much sediment, and they get smothered. Too little current, and food does not arrive often enough. Too steep, and attachment becomes risky. Too flat, and drifting particles may simply pass overhead. Each colony is the result of a very specific set of conditions lining up just right, like a cosmic baking recipe that only works at one exact angle in total darkness. Despite their fragile appearance, these corals are surprisingly resilient within their narrow comfort zone. Their skeletal structures are strong enough to withstand steady currents, and their tissues are adapted to cold temperatures that would slow down most biological processes. Everything about them is tuned for energy efficiency. There is no wasted motion, no flashy growth spurts, no unnecessary complexity. They are biological minimalists, surviving on crumbs while building monuments. There is also something quietly absurd about the whole setup. Here, on the edge of one of the deepest places on Earth, in water so dark it makes midnight feel optimistic, life has decided to build reefs. Not just survive, but construct elaborate frameworks that take centuries to assemble. It is as if the ocean looked at impossible conditions and said, yes, but what if we made furniture? These slope-dwelling corals challenge our assumptions about where complex ecosystems can exist. They show that reefs are not defined by sunlight or shallow water, but by structure, patience, and the steady flow of food. Along the Philippine Trench slopes, they stand as pale, silent architects, farming crumbs in the dark, proving that even in the most extreme environments, life finds a way to build something lasting, one tiny bite at a time. If corals are the architects of the trench slopes, deep-sea sponges are the custodians. They do not build dramatic branching towers or sprawling frameworks. They simply arrive, attach themselves to bare rock, and begin one of the longest, slowest jobs on Earth, filtering the ocean. On the steep faces of the Philippine Trench slopes, sponges cling to hard surfaces, like stubborn decorations no one has managed to remove for hundreds or even thousands of years. At first glance, sponges barely look alive. They resemble vases, fans, lumps, or abstract sculptures that seem more suited for a modern art museum than a living ecosystem. Some are shaped like delicate goblets, others like branching trees made of glass, and some like irregular blobs that appear to have given up on symmetry entirely. But beneath that quiet exterior is a remarkably efficient system designed for one purpose: moving water. Sponges survive by pumping seawater through their bodies. Tiny pores draw water in, internal channels guide it through a maze of chambers, and specialized cells capture microscopic food particles along the way. Bacteria, organic debris, and dissolved nutrients are removed, and cleaner water exits through larger openings. This process happens continuously, day and night, without rest. A single sponge can filter thousands of liters of water per day, which sounds impressive, until you remember that it has absolutely nothing else planned. The trench slopes offer ideal real estate for these organisms. Hard rock faces exposed by geological activity provide stable attachment points, while steady currents deliver a constant flow of water to filter. Unlike animals that need to move to find food, sponges let the environment do the traveling for them. Their entire existence depends on staying put and letting the ocean come by. It is a lifestyle that requires extraordinary patience and a total lack of ambition, biologically speaking. What truly sets deep-sea sponges apart is their longevity. Many species grow incredibly slowly, adding just fractions of a millimeter per year. Some individuals living on trench slopes may be several centuries old, possibly even longer. They began filtering water before entire human civilizations rose and fell, and they will likely continue long after modern cities become archaeological trivia. These sponges are not just animals, they are time capsules. Their internal structures are just as fascinating as their age. Some deep-sea sponges build skeletal frameworks from silica, forming intricate lattice patterns that resemble spun glass. These structures provide strength without bulk, allowing the sponge to maintain its shape while resisting currents. Others incorporate calcium-based elements or flexible protein fibers, depending on the demands of their environment. Each design reflects millions of years of trial and error, refined into forms that work exceptionally well at doing almost nothing quickly. Sponges also play a subtle but crucial role in shaping their surroundings. By filtering particles from the water, they influence local nutrient availability. Their waste products release processed organic material back into the environment, making nutrients accessible to other organisms. In this way, sponges act as biological recyclers, transforming diffuse resources into something usable. It is not glamorous work, but ecosystems depend on it. Someone has to take out the trash, and then the sponges volunteered before anyone else could object. Anchored to steep walls, sponges experience conditions that would challenge most life forms. Currents can be strong and unpredictable, temperatures remain cold, and food arrives in tiny, inconsistent quantities. Sponges respond by keeping their energy demands low. They do not chase prey, flee predators, or compete aggressively for space. They simply endure, adapting their growth to match what the environment can support. When resources are scarce, growth slows even further, stretching their already long lives even longer. There is also something quietly humorous about the contrast between their importance and their demeanor. Sponges are foundational to many deep-sea communities, yet they sit there doing their job with the enthusiasm of a dishwasher running on the quiet setting. No flashy displays, no dramatic behavior, just relentless filtration. If the ocean had a cleaning crew, sponges would be the ones working overnight. Unnoticed, but absolutely essential. Along the slopes of the Philippine Trench, these sponges turn bare rock into living surfaces. They provide texture, shelter, and chemical complexity to environments that might otherwise be stark. Their presence signals stability, patience, and the kind of success that does not rush. In a place defined by extreme pressure and constant darkness, deep-sea sponges remind us that survival does not always belong to the fastest or the strongest. Sometimes it belongs to the organism willing to sit still, filter quietly, and outlast everyone else by several hundred years. As we move along the trench slopes, the scenery suddenly gets legs. Small ones, many of them, clicking and gripping their way across rock faces and sediment patches. Squat lobsters and deep-water crabs are among the most visible residents of these slopes, and they look like creatures designed specifically to ignore gravity's complaints. Their bodies are compact, their limbs are strong, and their claws are perfectly suited for grabbing whatever the slope decides to offer that day. Squat lobsters are not true lobsters, despite the name. They are closer relatives of crabs, sporting flattened bodies and long, often spindly claws that extend like antennae searching for opportunity. On the trench slopes, they perch on ledges, wedge themselves into cracks, and cling to surfaces that seem wildly impractical for standing still. Their legs end in hooked tips that help them anchor against currents and steep angles, turning near vertical walls into usable dining space. Deep water crabs share a similar talent for making cliffs feel like living rooms. Their bodies are often broader and more robust, built to withstand the constant pressure and resist being swept away. Many species have reinforced shells and joints adapted for cold temperatures, where materials tend to become brittle. Down here, flexibility matters. A cracked shell is not a minor inconvenience. It is an invitation to disaster. Food on the trench slopes does not come neatly packaged. Squat lobsters and crabs survive by being opportunistic, which is a polite way of saying they will eat almost anything that does not eat them first. Organic debris drifting down the slope, scraps left behind by other animals, bits of plant material, and then even microbial films coating rocks all qualify as dinner. Their feeding habits turn the slope into a recycling zone where nothing edible stays uneaten for long. These crustaceans are especially good at exploiting the slope's geography. Gravity works in their favour, funneling material downhill and concentrating it in cracks, depressions, and along ledges. Where the terrain slows falling debris, scavengers gather. Squat lobsters often congregate in surprising numbers, forming loose assemblies that look like underwater traffic jams, all waiting for the next edible delivery. It is less a coordinated effort and more a shared understanding that patience usually pays off. Movement along the slopes requires careful engineering. Walking is not straightforward when down is always trying to pull you off the edge. These animals move with deliberate, controlled motions, maintaining multiple points of contact with the surface. Their center of gravity stays low, and their limbs act like built-in safety lines. Watching them navigate steep walls feels like observing expert climbers who never learned what falling is. Behaviorally, squat lobsters and crabs tend to balance boldness with caution. Food is scarce enough that hesitation can mean missing a meal. But predators do exist, and the slope offers limited escape routes. Many species rely on camouflage, blending into the rock and sediment with muted colours and textured shells. Others freeze in place when threatened, counting on stillness to make them invisible in the darkness. It is a strategy that works surprisingly well when visibility is already terrible. Reproduction. In this environment, adds another layer of challenge. Mates are not always easy to find, and encounters can be rare. Some species rely on chemical signals to locate one another, releasing cues into the water that drift along the slope. Others take advantage of gathering spots where food tends to accumulate, increasing the odds of crossing paths. Every successful encounter represents a small victory against isolation. What makes these crustaceans particularly important is their role as middle managers of the deep-sea food system. They are not at the bottom, and they are not at the top. They connect the dots, transferring energy from drifting debris into forms that larger predators can use. Without them, edible material would pile up or drift away unused, and the slope would be a much quieter, less dynamic place. Yes, there is also something deeply satisfying about their existence. Faced with sheer drops, crushing pressure, and limited food, evolution responded by creating creatures that treat cliffs like dining rooms. Squat lobsters and deep water crabs embody the idea that if there is food somewhere inconvenient, something will evolve to sit there and eat it. Along the slopes of the Philippine Trench, they scuttle, cling, and feast, turning a near vertical world into a surprisingly functional buffet table. At first, they are easy to miss. Along the sediment-covered stretches of the trench slopes, these animals blend in so perfectly that they look less like creatures and more like misplaced furniture. Sea cucumbers do not scuttle, dart, or chase. They inch, slowly, patiently, with the quiet determination of something that has all the time in the world and no intention of using it quickly. And yet, beneath that unhurried exterior lies one of the most important cleanup operations on the trench slopes. Sea cucumbers are echinoderms, relatives of sea stars, but they traded spiky arms for soft, elongated bodies that seem almost comically unsuited for extreme environments. On the slopes of the Philippine Trench, however, these animals are masters of sediment. They move across the seafloor using rows of tube feet, gripping and releasing grains one tiny step at a time. Progress is slow enough that watching one cross a meter of ground can feel like a long-term commitment. Their feeding strategy is elegantly simple. Sea cucumbers consume sediment, not accidentally, not occasionally, but deliberately. Using tentacle-like structures around their mouths, they scoop up mud and sand, ingest it, and extract whatever organic material is mixed in. Microscopic algae remnants, bacteria, decomposed plant matter, and tiny fragments of animal tissue are all filtered out during digestion. What remains is clean sediment, expelled behind them in tidy, compact piles. It is like watching the world's least exciting factory line, except the product is a healthier ecosystem. The slopes provide an ideal feeding ground for these animals. Gravity constantly pulls organic debris downhill, where it settles into the sediment. Over time, this material becomes mixed and buried, creating a buffet of low-energy food spread across the seafloor. Sea cucumbers specialize in extracting value from this seemingly worthless mixture. Where other animals might starve, they find enough nutrition to survive, grow, and reproduce, all while improving the sediment for everyone else. Life, under immense pressure, requires specialized biology, and sea cucumbers have adapted in fascinating ways. Their bodies lack rigid skeletons, relying instead on flexible tissues supported by microscopic structures embedded in their skin. This allows them to withstand pressure without cracking or collapsing. Their internal organs are arranged to tolerate compression, and their metabolism runs efficiently at low temperatures. In a sense, their softness is their strength. Nothing to snap, nothing to shatter. One of the most remarkable aspects of slope-dwelling sea cucumbers is their tolerance for low oxygen conditions. Sediment layers can become oxygen poor as organic material decomposes, but these animals are equipped to handle it. Their respiratory structures can extract oxygen from water with impressive efficiency, allowing them to persist where other species might struggle. This makes them well suited to the slow, steady life of sediment processing along the slopes. Their presence has a measurable impact on the seafloor. By constantly reworking sediment, sea cucumbers prevent it from becoming compacted and stagnant. This mixing, known as bioturbation, helps redistribute nutrients and oxygen, supporting microbial communities and improving conditions for other organisms living within or on top of the sediment. In other words, sea cucumbers are ecosystem engineers, even if they look like overgrown sausages with commitment issues. Defense for sea cucumbers is not about speed or aggression. Predators are relatively rare on the slopes, but when danger does appear, these animals rely on chemical deterrents and, in some species, dramatic stress responses. While not all deep-sea species share the more theatrical defenses of their shallow water relatives, many still produce substances that make them unappealing to eat. It is a reminder that even the most passive-looking organisms have lines they would prefer not to see crossed. Reproduction along the trench slopes is another exercise in patience. Many sea cucumbers release eggs and sperm into the water, relying on currents to bring them together. Success depends on timing and proximity, which can be challenging in sparsely populated environments. When it works, larvae drift before eventually settling onto suitable sediment, beginning the slow crawl toward adulthood. No rush, and no shortcuts. There is something deeply reassuring about sea cucumbers on the trench slopes. In an environment defined by extremes, they represent continuity and balance. They take what falls, extract what they need, and return the rest in better condition than they found it. They do not dominate the landscape or draw attention to themselves. They simply keep moving, inch by inch, cleaning the deep sea one mouthful of mud at a time. Along the rocky ledges of the trench slopes, where hard surfaces meet moving water, the scene suddenly looks more animated. Thin arms unfurl, curl and sway, reaching into the darkness with slow, deliberate grace. Brittle stars and feather stars are the masters of this space, turning exposed rock faces into feeding platforms suspended above the deep. They are echinoderms, like sea cucumbers, but they have chosen a very different strategy for survival. Instead of eating the ground, they harvest the water itself. Brittle stars resemble delicate starbursts anchored to the rock by a small central disk. From this hub extend long, flexible arms, each capable of independent movement. These arms are covered in tiny spines and tube feet that help capture passing food particles. Feather stars, by contrast, look like living fans or underwater fireworks frozen mid-explosion. Their many feathery arms branch repeatedly, creating an intricate net designed to intercept whatever the current delivers. Positioning is everything for these animals. They settle on elevated surfaces where water flow is consistent, such as the edges of terraces or the faces of protruding rocks. Currents sweeping along the trench slopes carry microscopic plankton, organic fragments, and nutrient-rich particles. Brittle stars and feather stars spread their arms wide, maximizing surface area and letting physics do most of the work. Feeding becomes a passive affair, less like hunting and more like holding out a net and waiting. Despite their fragile appearance, these animals are remarkably tough. Brittle star arms are built for flexibility, capable of bending without breaking even when currents shift suddenly. If an arm is damaged or lost, it can often be regenerated over time. Feather stars, too, can shed arms under extreme stress, sacrificing a limb to survive another day. It is a strategy that values persistence over perfection, and it works very well in unpredictable environments. Movement, while limited, is not entirely absent. Brittle stars can crawl using coordinated arm movements, repositioning themselves if conditions change. Feather stars are more sedentary, but some species can detach and slowly drift to a new perch if their current supply dries up. Watching this happen feels like seeing a houseplant decide it wants better lighting and quietly relocate itself. Feeding mechanisms differ subtly between the two groups. Brittle stars use their arms to sweep particles toward their mouths, which are located on the underside of the central disc. Feather stars rely on ciliated grooves along their arms to transport captured food inward. In both cases, the process is continuous and efficient, designed to capitalize on whatever the water provides without wasting energy. In the deep sea, efficiency is not a preference. It is a requirement. The arms of these animals do more than just feed. They also play a role in sensing the environment. Sensitive to changes in water flow and chemical cues, brittle stars and feather stars can adjust their posture in response to shifting conditions. Arms may be raised higher when currents strengthen or folded partially when food becomes scarce. This constant fine-tuning allows them to remain productive, even as the slope environment subtly changes. Their presence adds motion to an otherwise still landscape. In the beam of a submersible's lights, their arms ripple and sway, creating the illusion of a living forest growing sideways from the rock. It is an effect that feels almost theatrical, which makes the street performer analogy oddly fitting. They stand in place, arms outstretched, hoping the next passing current will be generous. Ecologically, these animals occupy a unique niche. By feeding directly from the water column, they connect drifting nutrients to the rocky slope environment. Their waste products contribute to local nutrient cycles, supporting microbes and small organisms nearby. In this way, they act as conduits, translating passing resources into usable energy for the slope community. There is also an understated elegance to their survival strategy. While other animals roam or burrow, brittle stars and feather stars choose stillness and precision. They trust the currents, trust their arms, and trust time. Along the slopes of the Philippine Trench, they prove that sometimes the best way to survive in a harsh world is to pick a good spot, open your arms, and let the universe bring you dinner. Once you leave the safety of rocks and sediment and look out into the open water along the trench slopes, the atmosphere changes. This is no longer a place of attachment and waiting. This is a place of motion. Deep-sea fish cruise these slopes with a calm, unhurried confidence, moving through darkness as if they have memorized it. They do not dart or chase wildly. Energy is too precious for that. Instead, they glide, hover, and make deliberate turns, treating gravity as a suggestion rather than a rule. Many of these fish have bodies that seem almost unfinished by surface world standards. Their muscles are soft, their bones are lightly built, and their skin often appears loose or gelatinous. This is not poor design, it is optimization. In an environment where pressure is immense and food is scarce, dense, rigid skeletons are unnecessary weight. By reducing bone density and muscle mass, these fish achieve neutral buoyancy with minimal effort. Yet they can stay suspended in the water column without constant swimming, saving energy for when it actually matters. The slopes act as hunting grounds, corridors where prey and nutrients move between depths. Deep-sea fish patrol these areas, using the terrain as a reference point in an otherwise featureless world. Some stay close to the seafloor, following the contour of the slope like pilots hugging a mountainside. Others drift slightly above it, scanning for movement or chemical cues. Their large eyes, when present, are adapted to detect faint traces of light, but many species rely more heavily on senses beyond vision. Smell plays a critical role here. Water carries chemical signals far and wide, and deep-sea fish are exquisitely sensitive to them. And a single damaged organism upslope can release a plume of scent that draws fish from surprising distances. Lateral line systems, which detect vibrations and pressure changes in the water, help them perceive movement in total darkness. In this world, seeing is optional. Feeling is everything. Feeding strategies vary widely, but they share a common theme. Make it count. Some fish have enormous mouths relative to their body size, equipped with long, inward-pointing teeth. This allows them to swallow prey nearly as large as themselves, an important adaptation when meals are unpredictable. Others specialize in picking off smaller organisms, relying on stealth and precise timing. There is no room for picky eating. If it fits, and does not fight too hard, it qualifies. Movement along the slope requires fine control. These fish often use slow, undulating fin motions rather than powerful tail beats. This style of swimming produces minimal disturbance, allowing them to approach prey without advertising their presence. It also conserves energy, which is the deep-sea equivalent of money. Spend too much too fast, and you do not get another paycheck. Reproduction among slope-dwelling fish reflects the challenges of their environment. Encounters between individuals can be rare, so some species rely on chemical cues to locate mates. Others produce relatively few but well-developed offspring, investing heavily in each one. Eggs and larvae may drift for long periods before settling into suitable habitats, making survival a game of probabilities rather than guarantees. Every adult fish you see is the result of countless failed attempts that did not make it. Predation risk exists even here. Larger fish patrol the same slopes, and some species have evolved transparent or darkly pigmented bodies to reduce visibility. Others use biochemistry, producing unpalatable tissues that discourage attacks. Speed is rarely the primary defense. Avoidance and invisibility tend to work better when there is nowhere to hide. What makes these fish particularly striking is how alien they feel while being, undeniably, fish. They have fins, gills, and familiar outlines, but everything about them is softened, stretched, or exaggerated to suit life under pressure. Watching them move is like watching gravity take a coffee break. They float, adjust, and pivot with minimal effort, perfectly at home in a space where humans would feel hopelessly out of place. Along the slopes of the Philippine Trench, these deep-sea fish are the roaming observers, the quiet patrols that connect fixed communities to the wider ocean. They move between ledges and depths, carrying energy and information through their feeding and movement. In a world defined by darkness and pressure, they demonstrate that survival does not require brute force. Sometimes it just requires letting go of heaviness and learning how to drift with purpose. In the darkness of the trench slopes, light does not come from the sun. It comes from life itself. Bioluminescence turns the deep sea into a quiet constellation of flashes, glows, and pulses, each one carrying meaning in a world where vision is otherwise limited. Along the slopes of the Philippine Trench, this living light show is not decoration. It is communication, camouflage, deception, and survival rolled into one glowing package. Bioluminescence works through chemistry. Specialized cells produce light when certain molecules react in the presence of oxygen, releasing energy as a visible glow. The colors vary depending on the chemistry involved, but in the deep sea, blue dominates. Blue light travels farthest through water, making it the most efficient choice. Evolution, as usual, picked the option that works best and did not bother with anything flashy like red unless there was a very good reason. Glowing shrimp are among the most common light producers along the slopes. Small and often translucent, they generate brief flashes or steady glows from organs embedded in their bodies. These lights can serve multiple purposes. A sudden burst may confuse a predator, creating a momentary visual overload that allows the shrimp to escape. In other cases, the glow may help individuals recognize members of their own species in the darkness, a kind of biological name tag floating through the water. Some fish along the slopes take bioluminescence to a more elaborate level. Light-producing organs can be arranged in patterns along their bodies, turning them into moving signals. These patterns may help with species recognition, ensuring that the right fish finds the right partner. In a place where faces are hard to see and introductions are awkward, glowing patterns help avoid unfortunate misunderstandings. Other species use light more aggressively. Sudden flashes can startle prey, freezing it just long enough to be captured. In some cases, bioluminescent displays lure curious organisms closer, but mistaking the glow for food or safety. It is a risky trick, but one that works often enough to persist. The deep sea rewards creativity, especially when it comes with built-in lighting. Counter-illumination is another clever use of bioluminescence. Some animals produce light on their undersides that matches the faint ambient glow filtering down from above. This makes them nearly invisible when viewed from below, erasing their silhouettes. It is the biological equivalent of stealth mode, allowing fish and shrimp to blend seamlessly into the darkness. Predators looking up see nothing but more dark water, which is exactly the point. Producing light is not free. It costs energy, and in the deep sea, energy budgets are tight. This means bioluminescence is often used sparingly and strategically, where many organisms can control when and how brightly they glow, turning their lights on only when necessary. This ability to fine-tune light output reflects the precision with which life operates along the trench slopes. Waste is not tolerated, even when it comes to something as useful as light. The presence of bioluminescence also shapes behavior. Animals become attuned to flashes and glows, learning what they mean and how to respond. A sudden light might signal danger. A steady pattern might suggest a potential mate. Over evolutionary time, these signals become part of a shared visual language spoken entirely in photons. The slopes are quiet, but they are not dark in the way we imagine. They are full of messages written in light. There is something deeply poetic about this system. In an environment where sunlight cannot reach, our life invents its own illumination. It does not waste it. It does not show it off unnecessarily. It uses it with purpose. Every flash along the slope represents a decision, a moment where chemistry and survival intersect. Watching bioluminescent organisms along the trench slopes feels like witnessing the ocean thinking out loud. Light becomes a tool, a warning, a promise, or a lie. And in the absence of day and night, these living flashlights remind us that darkness does not mean emptiness. It simply means the rules for being seen have changed. If the deep sea had weather, marine snow would be its most reliable forecast. It does not thunder, it does not pour, and it never stops. Instead, it drifts, slowly, constantly, an endless fall of tiny particles descending from the surface world to the trench slopes below. It is made of dead plankton, bits of decaying plants, mucus, shed cells, and an impressive amount of fecal material. In short, it is the ocean's leftovers, and it is absolutely essential. Marine snow begins its journey far above the trench, in sunlit waters, where plankton bloom and life is comparatively fast and chaotic. When organisms die, excrete waste, or shed material, these fragments clump together into tiny flakes. Microbes colonize them, altering their composition and weight. Over time, the particles grow dense enough to sink, beginning a slow descent that can take days or even weeks. By the time they reach the trench slopes, they have been processed, repackaged, and made edible again. The slopes play a special role in this process. Unlike the flat abyssal plains below, angled terrain intercepts falling particles. As marine snow does not simply pass straight down into the depths. It settles, slides, and accumulates along the slopes, concentrating nutrients in ways that flat seafloors cannot. Gravity funnels this organic drizzle into ledges, depressions, and sediment fields, turning the slopes into collection zones for food. For deep-sea communities, marine snow is the primary energy source. It fuels life at every level, from microbes to larger animals. Even though each individual particle is tiny, the constant nature of the fall makes it reliable. This is not a feast and famine system. It is a slow trickle, a nutritional subscription service that never cancels, but also never upgrades your plan. Marine snow is not uniform. Its composition changes depending on what is happening at the surface. Seasonal plankton blooms, storms, and shifts in ocean currents all influence what eventually reaches the slopes. This variability adds complexity to deep-sea ecosystems, subtly affecting growth rates, reproduction, and community structure. Life here is tuned to these distant surface events, even though the organisms themselves will never see the sun. As marine snow settles, it becomes a hotspot for microbial activity. Bacteria break down complex organic molecules, releasing nutrients in forms that other organisms can use. This microbial processing transforms falling debris into something biologically accessible, essentially pre-digesting the deep sea's meals. The slopes, with their constant supply of particles and varied surfaces, provide ideal conditions for this microscopic workforce. The slow descent of marine snow also creates time. While unlike sinking carcasses or sudden food falls, marine snow allows organisms to feed continuously without expending energy searching. This shapes behavior and physiology. Many deep-sea animals are adapted to capture tiny particles efficiently, maximizing the value of each passing flake. Nothing is wasted. Even the smallest crumbs matter when they are all you get. There is an odd honesty to marine snow. It is not glamorous. It does not look impressive. Yet it underpins entire ecosystems. Without it, the trench slopes would be nearly lifeless. No dramatic predators, no intricate communities, no slow-growing giants. Everything depends on this quiet reign of decay. The deep sea runs on recycling, and marine snow is the delivery system. The slopes also influence how long marine snow stays available. Particles can be resuspended by currents, as settling again and again, before finally being consumed or buried. This repeated cycling increases the chances that organisms will encounter and use the material. In a place where food is scarce, extending the life of every particle is a major advantage. Understanding marine snow changes how we think about the deep ocean. It reveals a world connected to the surface, not by light, but by fallout. The trench slopes are not isolated voids. They are downstream from everything that happens above. Every bloom, every die-off, every excretion event eventually sends a message downward in the form of drifting debris. So while marine snow may be the least appealing name for a food source, it is the deep sea's lifeline. Along the slopes of the Philippine Trench, this constant drizzle feeds patience, resilience, and adaptation. It is proof that even in the darkest places on Earth, life survives not through abundance, but through the steady arrival of leftovers falling from the sky. Along the trench slopes, where rock faces rise like underwater cliffs, intelligence takes on a very specific shape. It is soft, flexible, and equipped with 8 extremely opinionated arms. Deep-sea octopuses are among the most intriguing predators in this environment, not because they are fast or heavily armed, but because they are clever. In a place where brute force is expensive and mistakes are fatal, thinking your way through problems becomes a powerful survival tool. These octopuses are built for the slope. Their bodies lack rigid skeletons, allowing them to squeeze into cracks, flatten against rock, and contour themselves to uneven surfaces. This flexibility lets them exploit the smallest hiding places, turning the rugged geography of the trench slopes into a three-dimensional hunting ground. If there is a crevice big enough for a thought, an octopus can probably fit into it. Movement is controlled and deliberate. Octopuses use a combination of arm crawling and gentle jet propulsion to navigate the slope walls. Each arm operates with a degree of independence, exploring the surface, tasting it, feeling for vibrations. Their suckers are packed with sensory cells, capable of detecting chemical signals, effectively allowing them to taste the environment through touch. Hunting here is not about chasing prey across open space. It is about searching, probing, and waiting for the right moment. Deep-sea octopuses feed on a variety of organisms found along the slopes, including crustaceans and other small invertebrates. When they locate prey, they rely on stealth rather than speed. An arm may slowly extend, making minimal disturbance, before pulling the target toward the beak, hidden at the center of the arms. The entire process is efficient and quiet, designed to avoid attracting attention from larger predators that might be watching. What truly sets octopuses apart is their problem-solving ability. Their nervous systems are highly developed, with a large portion of neurons distributed throughout the arms rather than centralized in the brain. This allows each arm to process information and respond independently, creating a decentralized intelligence that excels in complex environments. Along the trench slopes, this translates into an uncanny ability to navigate obstacles, manipulate objects, and adapt to changing conditions. Camouflage is another critical tool. Octopuses can change the color and texture of their skin in seconds, blending seamlessly into rock surfaces or sediment. Specialized skin cells expand and contract to alter patterns, while tiny muscular structures create bumps and ridges that mimic the surrounding terrain. On a slope where shadows and textures dominate, this ability turns octopuses into living optical illusions. Reproduction in such an extreme environment demands sacrifice. Many deep-sea octopuses invest heavily in their offspring, producing relatively few eggs and guarding them for extended periods. Females may attach eggs to rock surfaces along the slope and remain with them, aerating and cleaning them until they hatch. During this time, feeding may stop entirely, and it is a strategy that prioritizes quality over quantity, ensuring that at least some offspring begin life with a fighting chance. Octopuses also exhibit a remarkable tolerance for low-energy lifestyles. Their metabolism is adapted to cold temperatures and scarce food, allowing them to survive long periods between meals. When prey is abundant, they feed. When it is not, they wait. This patience is essential in a world where opportunities appear unpredictably. Despite their intelligence, octopuses remain vulnerable. Larger predators patrol the slopes, and an exposed octopus is an easy target. This risk reinforces their reliance on stealth, camouflage, and environmental awareness. Every movement is calculated, every decision weighed. Watching an octopus hunt along a trench wall feels less like observing an animal and more like watching a puzzle solve itself in slow motion. There is something profoundly human about their behavior. Curiosity, adaptability, and problem-solving are traits we recognize and admire. Yet here they are, thriving in total darkness under crushing pressure. Along the slopes of the Philippine Trench, deep-sea octopuses demonstrate that intelligence does not require sunlight or comfort. It only requires challenges worth solving. Along the trench slopes, motion takes on a different tone when sharks and rays appear. There is no sudden burst of speed, no dramatic chase. Instead, there is glide. Deep-sea sharks and rays move with an unhurried grace that feels almost ceremonial, as if they are aware that nothing down here is worth rushing. These animals are among the oldest lineages of vertebrates on Earth, and their presence along the slopes carries a sense of deep time that few other creatures can match. Deep-sea sharks tend to have streamlined bodies built for steady cruising rather than sprinting. Their muscles are adapted for endurance, not bursts of power. Many species possess large, oil-rich livers that help with buoyancy, reducing the energy required to stay afloat. This allows them to patrol the slopes efficiently, covering large areas in search of food without burning through precious calories. In an environment where meals are unpredictable, efficiency is survival. Rays, closely related to sharks, approach the slopes from a different angle. Their flattened bodies and wing-like pectoral fins are well suited for skimming close to the seafloor. And some glide just above sediment-covered areas, sensing buried prey through electroreception. Specialized organs detect faint electrical signals produced by the muscle activity of other animals, allowing rays to locate targets hidden from view. It is a hunting method that works perfectly in darkness, where eyesight alone would fail. Both sharks and rays share a slow pace of life. They grow gradually, mature late, and produce relatively few offspring. This strategy works in stable environments where survival rates are high and competition is limited. Along the trench slopes, where conditions change slowly and dramatic disruptions are rare, patience pays off. These animals are not built for rapid population booms. They are built to persist. Their sensory systems are finely tuned to the deep-sea environment. Smell remains a dominant sense, and capable of detecting trace chemicals over long distances. The lateral line system helps them perceive movement and pressure changes in the water, providing a three-dimensional awareness of their surroundings. Vision, while present, is adapted to low light, with eyes sensitive enough to detect faint contrasts rather than detailed images. Together, these senses create a comprehensive picture of the slope environment. Feeding strategies vary among species, but most deep-sea sharks and rays are opportunistic predators. They consume fish, invertebrates, and carrion when available. Instead of actively pursuing prey, many rely on stealth and surprise, approaching slowly before making a decisive strike. This minimizes energy expenditure and reduces the risk of injury. In the deep sea, even small wounds can be costly, so caution is a constant companion. Their role in the slope ecosystem is subtle but significant. As higher-level predators, they help regulate populations of other animals, preventing any one group from dominating. This balance contributes to the overall stability of the community. Unlike surface ecosystems, where predators often exert dramatic top-down control, deep-sea systems operate more quietly. The influence of sharks and rays is measured in long-term patterns, rather than immediate effects. What makes encounters with these animals particularly striking is their demeanor. They do not appear hurried or aggressive. They move as if they have already seen everything there is to see. This calm confidence is the product of evolutionary success stretched across hundreds of millions of years. Long before dinosaurs roamed land, the ancestors of modern sharks and rays were already navigating ancient seas, refining the same basic designs that still work today. There is also vulnerability beneath that confidence. Slow growth and low reproductive rates make deep-sea sharks and rays especially sensitive to disturbances. Their life histories leave little room for rapid recovery. Every individual represents decades of survival in a harsh environment, making their presence along the slopes all the more remarkable. Along the Philippine Trench slopes, these ancient animals serve as living reminders of the ocean's memory. They connect the present to a distant past, moving through darkness with the quiet authority of creatures that have endured countless planetary changes, watching them glide by. And it is easy to believe they know something we do not, that survival is not about speed or force, but about lasting long enough for the world to change around you. Beneath the visible life of the trench slopes lies a world so small and so strange that it often gets overlooked, despite quietly running the entire operation. Embedded within the sediments are vast communities of microbes, bacteria and archaea that thrive without sunlight, without plants, and without anything resembling a normal food chain. These organisms do not care that the sun is gone. They solved that problem a very long time ago. The sediments along the Philippine Trench slopes are not dead mud. They are layered, chemically active environments where minerals, gases, and organic remnants mix under intense pressure. Microbes occupy the tiny spaces between sediment grains, forming living networks that stretch across entire slope regions. Each grain of sediment can host millions of microorganisms, all conducting microscopic business transactions that keep deep-sea ecosystems functioning. Unlike surface life, which relies heavily on photosynthesis, these microbes use chemosynthesis. Instead of capturing energy from light, they extract energy from chemical reactions. Some oxidize sulfur compounds, others use methane, hydrogen, or iron as fuel. These reactions release energy that microbes use to grow and reproduce. It is metabolism stripped down to its most inventive form. No sunlight, no problem. The trench slopes are essentially powered by chemistry class. The slope environment is particularly suited to this kind of life. As organic material settles and becomes buried, it reacts with surrounding sediments, or producing chemical gradients. Oxygen disappears quickly below the surface, replaced by zones rich in alternative compounds. Microbes specialize in specific layers, each adapted to a narrow chemical niche. One group's waste becomes another group's fuel, creating a tightly linked chain of reactions that recycles matter with astonishing efficiency. These microbial communities operate on timescales that make patience look impulsive. Chemical reactions proceed slowly in cold temperatures, and microbial growth can be measured in months or years rather than hours. Yet the sheer number of microbes compensates for their slow pace. Collectively, they process enormous amounts of material, quietly controlling how nutrients move through the slope ecosystem. Their influence extends far beyond their size. By breaking down organic matter, our microbes release nutrients that support other forms of life. They regulate the chemistry of sediments, influencing which minerals form and which gases are released. In some areas, microbial activity can even affect the physical structure of sediments, subtly altering how compacted or porous they become over time. One of the most fascinating aspects of slope-dwelling microbes is their resilience. These organisms are adapted to extreme pressure, low temperatures, and limited energy availability. Their cell membranes are structured to remain stable under crushing conditions. Their enzymes are tuned to function efficiently in cold environments. Everything about them reflects a long evolutionary history of making do with less. Microbial diversity along the slopes is immense. Many species have never been cultured or studied in detail, are known only through genetic traces extracted from sediment samples. Each discovery hints at metabolic strategies that push the boundaries of what life can do. Some microbes may survive on energy yields so low that they barely sustain cellular processes, existing in a state of near suspended animation. Life, in these cases, becomes less about thriving and more about persisting. there is also a philosophical weight to their existence. These microbes demonstrate that life does not need warmth, light, or abundance. It needs opportunity, even if that opportunity comes in the form of trace chemicals locked inside cold mud. Along the trench slopes, they form the foundation upon which everything else depends. Without them, organic material would accumulate unused, nutrients would remain locked away, and higher life would struggle to survive. So, in a very real sense, microbial life is the engine of the trench slopes. Larger animals may capture our attention, but microbes do the heavy lifting. They recycle, regulate, and sustain the system from the bottom up. Every shrimp, fish, or octopus ultimately depends on processes carried out by organisms too small to see. So while they lack dramatic shapes or glowing displays, these sediment-dwelling microbes represent one of the most impressive achievements of evolution. They prove that life does not require sunlight or even comfort. It requires creativity, persistence, and the ability to turn chemistry into survival. On the slopes of the Philippine Trench, the smallest residents may also be the most essential, quietly rewriting the rules of what it means to be alive. Pressure is the quiet dictator of the trench slopes. Yet it does not announce itself with sound or movement, but it is always present, pressing inward from every direction with relentless force. Down here, pressure is not just a condition to tolerate, it is a design requirement. Every living thing on the slopes of the Philippine Trench exists because its biology has been rebuilt from the inside out to handle being squeezed by the weight of the ocean. At extreme depths, pressure interferes with the most basic processes of life. Proteins, which need to fold into precise shapes to function, can be distorted or destabilized. Cell membranes, which must remain flexible but intact, risk becoming too rigid or too leaky. Enzymes, the molecular machines that drive metabolism, can slow down or stop entirely if their structure is altered. In short, her pressure threatens to turn life's delicate machinery into a pile of useless parts. Slope-dwelling organisms solve this problem at the molecular level. Their proteins are structured differently, with stronger internal bonds that help maintain shape under compression. These proteins are not stiffer in a way that makes them brittle. Instead, they are stabilized just enough to resist pressure while remaining flexible enough to do their jobs. It is a balancing act refined over millions of years, where too much rigidity is just as dangerous as too little. Cell membranes undergo their own redesign. In surface organisms, membranes are composed of fatty molecules arranged to create a semi-fluid barrier. Under high pressure, these membranes can become too rigid, interfering with transport and communication between the inside and outside of the cell. Deep-sea organisms adjust the composition of their membranes, incorporating specific types of fats that maintain fluidity, even when squeezed. Think of it as swapping butter for oil, so things still move when the fridge gets very cold. Except the fridge is an entire ocean. Enzymes, which control chemical reactions, are also pressure specialists. In slope-dwelling species, enzymes are adapted to function efficiently under compression and low temperatures. Their shapes are fine-tuned so that pressure does not prevent them from binding to their target molecules. This ensures that metabolism continues smoothly, even when environmental conditions would shut down similar processes at the surface. Life here runs on precision engineering at the nanoscale. Pressure also influences how cells communicate and transport materials. Channels and pumps embedded in cell membranes must operate reliably, moving ions and molecules in and out. These structures are reinforced and adapted to resist deformation. Without this, basic processes like nerve signaling or muscle contraction would fail. Every heartbeat, every movement, depends on components that can withstand being crushed without complaint. Interestingly, pressure adaptation is not about brute strength. Cells do not become thicker or heavier to resist compression. Instead, they become smarter. They use chemistry and structure to neutralize pressure's effects, effectively pretending it is not there. This strategy saves energy and allows organisms to remain lightweight and efficient, which is essential in environments where food is limited. Pressure also affects how genetic material behaves. DNA and the proteins that manage it must remain stable and accessible. Deep-sea organisms have adaptations that protect these systems, ensuring that cells can still divide, repair damage, and respond to environmental changes. Without this molecular resilience, long-term survival would be impossible. What makes these adaptations especially remarkable is that they are invisible. You cannot look at a deep-sea animal and see pressure resistance the way you can see claws or fins. It exists at a scale far smaller than our senses can detect. And yet, it defines everything. Remove these molecular safeguards, and life on the trench slopes would collapse instantly, not dramatically, but quietly, at the level of chemistry. There is a strange elegance to this. Rather than fighting pressure, as life on the slopes accommodates it. Instead of building armor, it builds stability. Instead of resisting, it adapts. This approach reflects a broader theme of deep-sea survival. Success comes from harmony with extreme conditions, not opposition to them. So when we watch animals drifting, crawling, or clinging along the slopes of the Philippine Trench, we are seeing the visible result of countless invisible adjustments, proteins holding their shape, membranes staying fluid, enzymes doing their jobs without complaint. Pressure may rule this world, but life has learned its laws and rewritten itself accordingly, refusing to collapse even when the ocean leans in with its full weight. Reproducing on the trench slopes is a logistical challenge that would make event planners cry. There is no predictable food supply, no obvious seasons, and potential mates may live far apart in a vast, dark landscape. And yet, life persists, generation after generation. The species that inhabit the slopes of the Philippine Trench have evolved reproductive strategies that reflect patience, timing, and a deep understanding of uncertainty. One of the most common strategies is broadcast spawning. In this approach, individuals release eggs and sperm into the surrounding water, relying on currents to mix them together. It is a gamble, but one that works when populations are spread over large areas. Timing is everything. Many species synchronize spawning events to maximize the chance that reproductive cells meet. Chemical cues, environmental signals, and internal biological clocks help coordinate these releases, turning the water column into a temporary meeting place. While broadcast spawning produces large numbers of eggs, but survival rates are low. Most larvae will never make it to adulthood. This is not failure. It is strategy. By producing many offspring, species hedge their bets against an unpredictable environment. Even if conditions are poor one year, a few survivors may find the right combination of food and habitat to continue the lineage. In the deep sea, success is measured over long timescales, not individual lifetimes. Other slope-dwelling species take a more cautious approach through brooding. Instead of releasing eggs into the open water, they protect them on or within their bodies. This may involve attaching eggs to hard surfaces, carrying them in specialized structures, or guarding them until they hatch. Brooding reduces the number of offspring produced, but dramatically increases the chances that each one survives. It is a strategy well suited to environments where resources are limited and offspring cannot afford a rough start. Brooding often comes at a cost. Parents may reduce feeding, mobility, or growth while caring for eggs. In some cases, brooding lasts for months, even years. This level of investment reflects how valuable each offspring is. When energy is scarce, quality outweighs quantity. Each young individual represents a significant commitment of time and resources, and losing one is not easily replaced. Larval life adds another layer of complexity. Many species produce larvae that drift in the water before settling onto the slope. This drifting phase allows offspring to disperse, reducing competition with parents and increasing the chances of finding suitable habitat. And however, it also exposes larvae to hazards and uncertainty. They must feed, avoid predators, and eventually settle in the right place at the right time. It is a journey defined by chance and resilience. Some slope species bypass a long larval phase altogether, producing offspring that resemble miniature adults. These young settle quickly and begin life on the slope immediately. This approach limits dispersal, but increases early survival. It works best in stable environments where local conditions are known to support life. Again, there is no single best strategy, only strategies that work under specific circumstances. Environmental cues play a subtle but crucial role in reproduction. Changes in water chemistry, temperature, or food availability can trigger reproductive activity. Even distant events at the surface, such as seasonal plankton blooms, can influence timing. Slope species have evolved to read these cues, aligning reproduction with periods when conditions are slightly more favorable. It is a delicate dance, performed without calendars or alarms. What all these strategies share is an emphasis on efficiency and timing. There is no room for waste. Reproductive efforts must align with moments when energy is available and survival odds are highest. This makes reproduction in the deep sea feel less like an annual event and more like a carefully planned operation executed whenever conditions allow. Along the slopes of the Philippine Trench, reproduction is not flashy or frequent. It is quiet, deliberate, and deeply strategic. Every egg released, every brood protected, represents a calculated response to an environment that offers no guarantees. And in a world where dinner does not show up on a schedule, bringing new life into existence requires patience, precision, and a willingness to trust that somewhere in the darkness, the timing will be right. Every so often, the trench slopes receive an unexpected delivery. A fish dies upslope. A larger animal succumbs somewhere above. Gravity takes over, and the remains begin their slow, tumbling descent. This is not a tragedy in the deep sea. It is an event. And almost immediately, scavengers arrive. Amphipods, small shrimp-like crustaceans, are among the fastest responders, materializing from the darkness with the enthusiasm of creatures that absolutely do not skip meals. Amphipods are built for this lifestyle. Their bodies are laterally compressed, allowing them to slip easily through tight spaces in the sediment or water column. Strong legs propels them quickly toward food sources, while sensitive antennae detect chemical signals released by decaying tissue. Even tiny amounts of scent can travel far in deep water, and amphipods are remarkably good at following these invisible trails. When a carcass lands on the slope, it is only a matter of time before they find it. What makes their appearances so striking is the speed. Within minutes to hours, amphipods can gather in astonishing numbers, covering a carcass in a writhing mass of bodies. This sudden abundance feels almost supernatural, as if the slope itself produced them. In reality, they were already there, spread thin across the environment, waiting for an opportunity worth moving for. Food falls act like beacons, pulling scavengers in from all directions. Once assembled, amphipods get to work, and they tear into soft tissue with specialized mouthparts, breaking down large remains into smaller fragments. This rapid consumption serves an important ecological function. It prevents valuable organic material from being lost to the depths unused. Instead, energy is quickly transferred into the scavenger community, where it can be redistributed through the food web. Competition during these feeding events is intense. Amphipods jostle for position, climb over one another, and feed continuously. There is no polite sharing. The faster you eat, the better your chances. This chaotic scene may look inefficient, but it ensures that resources are processed quickly. In a place where food is unpredictable, speed matters when opportunity strikes. Amphipods are also adapted to handle the biochemical challenges of decay, as carcasses can become chemically harsh environments as decomposition releases compounds that deter other organisms. Amphipods tolerate these conditions well, allowing them to exploit resources that might otherwise go untouched. Their digestive systems are equipped to handle nutrient-rich but potentially toxic meals, turning rot into fuel. After the initial feeding frenzy, other scavengers may arrive, but amphipods often remain until little is left. Bones, tougher tissues, and fragments are gradually reduced, leaving behind a stripped-down version of what once was. Eventually, the site returns to relative quiet, but the effects linger. Nutrients released during the process enrich the surrounding sediment, supporting microbial activity and future life. Amphipods themselves are not just consumers, they are also prey. As their sudden population spikes attract predators, creating temporary hotspots of activity along the slope. This makes food falls important, not only as feeding events, but as moments of ecological connection. Energy moves rapidly through multiple levels of the ecosystem, linking death to life in a very direct way. Reproduction in amphipods is well suited to this boom and bust lifestyle. Many species reproduce relatively quickly, with broods developing inside protective structures until they are ready to emerge. This allows populations to rebound after periods of scarcity and take advantage of feeding events when they occur. Flexibility and responsiveness are key to their success. There is something oddly celebratory about these scavenging swarms. They remind us that in the deep sea, nothing is wasted. Death is not an endpoint, but a transfer. Along the slopes of the Philippine Trench, amphipods embody this principle with unmatched efficiency. They appear without warning, eat with purpose, and vanish just as quickly, leaving behind a cleaner seafloor and a reminder that even in the darkest places, life is always ready for the next meal. When we think about migration, we usually picture animals moving across vast distances, traveling from one place to another across the surface of the planet. On the trench slopes, migration works differently. Here, movement often happens up and down rather than across. The steep descent of the Philippine Trench creates a continuous vertical pathway, allowing species to shift depth without ever leaving the same general location. It is less like a road trip and more like using an elevator that spans entire ecological worlds. The slope acts as a bridge between environments that would otherwise be isolated. Shallow continental regions and the deep ocean are separated by dramatic changes in pressure, temperature, and light. On flat seafloors, transitioning between these zones would require long horizontal journeys. Slopes compress these gradients into relatively short distances, making it possible for animals to move gradually from one set of conditions to another. This gradual change is crucial. It allows species to adapt step by step, rather than facing abrupt environmental shifts. For some animals, vertical movement is a daily routine, They adjust their depth to follow food or avoid predators, using the slope as a reference point. Others move seasonally or over the course of their lives, occupying different depths at different stages. Juveniles may settle in shallower parts of the slope, where conditions are slightly less extreme, then move deeper as they grow and their physiology changes. The slope becomes a lifelong pathway, guiding development as well as movement. This vertical connectivity has profound ecological consequences. It allows energy and nutrients to move between depth zones, carried by migrating animals. When organisms feed in one area and release waste or die in another, they transport resources across the slope. In this way, the trench slopes function as conduits, redistributing energy throughout the deep sea system. Without these connections, ecosystems would be far more isolated and less resilient. The slope highway also influences evolution. Species that can tolerate a range of depths have more opportunities to spread and diversify. Over time, our populations may adapt to different sections of the slope, eventually becoming distinct species. The slope thus acts as both a corridor and a divider, facilitating movement while encouraging specialization. It is a dynamic landscape where evolutionary experiments play out vertically rather than geographically. Movement along the slope is not without challenges. Pressure increases rapidly with depth, and temperature drops. Animals that use the slope as a pathway must possess physiological flexibility, allowing them to function across changing conditions. This often means gradual movement, rather than sudden shifts. The slope's continuous nature supports this, offering intermediate zones where organisms can pause, adjust, and continue when conditions allow. Predation and competition also shape how species use the slope highway. Certain depths may be safer at specific times, prompting animals to move accordingly. Others may follow prey distributions that change with depth. The slope becomes a three-dimensional chessboard, where position matters and movement is strategic. Knowing when and where to move can mean the difference between survival and becoming someone else's dinner. The idea of slopes as highways also challenges how we think about deep-sea isolation. Rather than being cut off from the rest of the ocean, trench slopes integrate deep environments into a larger system. They allow for genetic exchange, species turnover, and ecological interaction across depths. This connectivity helps explain why deep-sea communities are more dynamic than they might appear. From a human perspective, this vertical movement is easy to overlook. We tend to map ecosystems horizontally, drawing boundaries across surfaces. The trench slopes remind us that the ocean does not follow our maps. It is layered, connected, and constantly in motion, even in places that seem still. Along the slopes of the Philippine Trench, animals move not because they are migrating to somewhere new, but because the slope itself offers opportunity. It is a pathway carved by geology, used by biology, and essential to the deep sea's functioning. In a world defined by depth, the slopes are the roads that keep life connected, allowing ecosystems to breathe, adapt, and endure across the vertical dimension of the ocean. It is tempting to imagine the trench slopes as untouched wilderness, too deep, too dark, and too extreme for human influence to reach. Unfortunately, that illusion does not hold up under close inspection. Even along the steep walls of the Philippine Trench, signs of human activity appear, subtle but unmistakable. Our presence arrives not with footsteps or buildings, but with objects that do not belong, drifting down from the surface and settling into places we will never personally visit. One of the most visible impacts comes from deep-sea fishing debris. Lost nets, lines, and traps can travel vast distances before sinking, eventually snagging on the slopes. The steep terrain acts like a catcher's mitt, trapping this equipment as it slides downward. Once lodged, these materials may remain for decades, slowly degrading but never truly disappearing. Synthetic fibers do not break down easily in cold, dark environments, turning the slopes into long-term storage sites for forgotten gear. These abandoned fishing materials continue to interact with the ecosystem long after they are lost. Nets can entangle animals, restricting movement or causing injury. Lines draped across rock faces create obstacles in environments where navigation already requires precision. Even small fragments can interfere with feeding or attachment for organisms that rely on clean surfaces. The slopes, once shaped solely by geology and biology, now include human-made hazards. Microplastics represent a quieter but far more pervasive problem. Tiny fragments of plastic enter the ocean through countless pathways, from degraded consumer products to synthetic fibers shed from clothing. These particles are small enough to remain suspended for long periods, eventually settling into deep-sea sediments or becoming embedded in biological tissues. Yes, along trench slopes, microplastics accumulate in sediments and within organisms that feed on drifting or deposited material. Once microplastics enter the deep-sea food web, their effects become difficult to trace, but impossible to ignore. Small organisms ingest them accidentally, mistaking them for food. These particles can pass through digestive systems, but they may also carry chemicals that leach into tissues. As predators consume prey, plastics move up the food chain, spreading through the ecosystem. Even in the most remote environments on Earth, the signature of human production is now present. The physical structure of the slopes amplifies these impacts. Steep angles concentrate falling debris, funneling it into specific areas rather than dispersing it evenly. What might be a scattered problem on flatter seafloors becomes more focused along trench walls and terraces. This increases the likelihood that organisms will encounter human-made materials, turning isolated incidents into persistent features of the landscape. There is also the issue of disturbance. While large-scale mining has not yet transformed these specific slopes, exploratory activities and research equipment can still leave traces. Even careful scientific exploration introduces foreign materials and noise into environments that evolved without them. The challenge lies in balancing the need to understand these ecosystems with the responsibility to minimize our footprint. Perhaps the most unsettling aspect of human impact on trench slopes is its invisibility to us. These environments are out of sight, far beyond daily experience. The damage does not wash up on beaches or appear in headlines. It accumulates quietly, in places few people will ever see. This distance makes it easy to forget that our actions at the surface ripple downward, reaching even the planet's deepest edges. The organisms living on the slopes have no evolutionary history with plastic or synthetic fibers. They cannot adapt quickly to these materials, nor can they remove them. What arrives from above becomes part of their environment by default. In ecosystems built on efficiency and patience, these intrusions represent unnecessary complications imposed by a species that does not have to live with the consequences. Acknowledging human impact on the trench slopes is uncomfortable, but necessary. It reminds us that no place on Earth is truly isolated from global systems of production and waste. Here, the deep sea is not a separate world. It is downstream from everything we do. Along the slopes of the Philippine Trench, life continues to adapt, filter, scavenge, and survive, even as human-made debris becomes another environmental factor to contend with. The presence of our mess in such remote places serves as a stark reminder. Exploration and responsibility must go hand in hand, because even the deepest cliffs in the ocean are now part of the human story. Studying the trench slopes is not a matter of grabbing scuba gear and enthusiasm. These environments exist far beyond the reach of human bodies, and the only reason we know anything about them at all is because we send machines in our place. Remotely operated vehicles, or ROVs, are the deep sea's visiting journalists, and descending slowly along the slopes to document a world that would otherwise remain invisible. An ROV is essentially a robotic explorer tethered to a research vessel by a long cable that supplies power and transmits data. This tether is both a lifeline and a limitation. It must be strong enough to withstand immense pressure and flexible enough to follow the vehicle as it navigates steep terrain. Pilots on the surface guide the ROV using joysticks and screens, relying on cameras and sensors to see through the darkness thousands of meters below. Navigating the trench slopes is particularly challenging. The terrain is uneven and unpredictable, with sudden drop-offs, protruding rocks, and sediment clouds that can obscure vision. Pilots must maneuver carefully to avoid collisions or entanglement. Every movement is deliberate, slow, and precise. There are no quick corrections down here. If something goes wrong, recovery is measured in hours, not seconds. The cameras mounted on ROVs are the stars of the operation. High-definition video allows scientists to observe animals in their natural habitats, capturing behaviors that would never be seen in samples hauled to the surface. These cameras are paired with powerful lights, which slice through the darkness and reveal scenes that often look unreal. Translucent bodies, glowing organs, and unfamiliar shapes drift into view, looking more like movie props than living creatures. Despite the spectacle, the animals themselves often seem unimpressed. Many continue their routines, ignoring the strange glowing visitor. Others react briefly, retreating into cracks or drifting away. These reactions provide valuable information about behavior, movement, and habitat use. Observation without disturbance is a central goal, and ROVs are designed to minimize noise and water movement as much as possible. Beyond cameras, ROVs carry a suite of scientific instruments. Manipulator arms allow them to collect samples of sediment, water, or organisms with surprising delicacy. Sensors measure temperature, chemistry, and currents, building a detailed picture of the environment. Together, these tools allow scientists to connect what they see to the conditions shaping it. A strange animal becomes more than a curiosity. It becomes part of a larger system. ROVs also help map the slopes themselves. Sonar systems generate detailed images of the seafloor, revealing terraces, walls, and channels invisible to the naked eye. These maps provide context, and showing how biological communities align with geological features. Understanding the shape of the slope is essential for interpreting everything else that lives there. One of the most important contributions of ROV exploration is documentation. Video footage creates a permanent record of deep-sea life, allowing scientists to revisit observations, share findings, and compare changes over time. This is especially valuable in environments where direct access is limited. Each dive adds to a growing archive of knowledge, piecing together a picture of the trench slopes one frame at a time. There is also a human element to these missions. Teams of scientists, engineers, and pilots work together for long hours, watching screens as the ROV descends into darkness. Moments of discovery are shared in real time, often accompanied by a mix of excitement and disbelief. When an unfamiliar organism appears, it can feel like meeting an alien, except this alien has been quietly living on Earth all along. ROVs have transformed our understanding of the deep sea, turning inaccessible depths into observable ecosystems. Without them, the trench slopes would remain largely theoretical, known only through indirect measurements. With them, we can watch life unfold in places once thought unreachable. Along the slopes of the Philippine Trench, these robotic explorers act as our eyes and hands, revealing a world that feels both distant and deeply connected to our own. The footage they capture reminds us that the ocean still holds countless surprises, and that even in the most extreme environments, life thrives in forms that challenge our imagination and politely ignore our cameras. When people imagine the deep ocean, they often picture emptiness, a vast, dark nothingness stretching endlessly downward. The slopes of the Philippine Trench challenge that idea completely. They are not empty. They are layered, complex, and quietly busy, filled with organisms that have turned extreme conditions into a perfectly livable neighborhood. Not comfortable by human standards, but then again, humans are famously bad at judging what counts as reasonable. These slopes exist in a realm where sunlight never arrives, pressure never lets up, and food arrives without warning. And yet, life has not only survived here, it has specialized. Every ledge, wall, and sediment patch supports organisms uniquely suited to that precise slice of the environment. As the result is not a single ecosystem, but a vertical mosaic, stacked layer upon layer down the trench wall. What stands out most about slope life is patience. Growth is slow. Movements are deliberate. Energy is spent carefully, like budgeting in a place where paychecks arrive at random. This patience allows life to persist where urgency would fail. There is no rush when rushing wastes fuel. There is no excess when efficiency keeps you alive. The deep sea does not reward speed. It rewards endurance. Weirdness is another defining feature, and it is not accidental. Evolution on the slopes has had millions of years to experiment, free from many of the pressures that shape surface life. The result is a collection of forms and behaviors that seem bizarre only because they are unfamiliar. Translucent bodies, unusual proportions, and unexpected solutions to everyday problems are normal here. On the slopes, weird is just another word for functional. These ecosystems also redefine what it means to be successful. There are no dominant species overwhelming the environment. Instead, success is measured by fitting in, by occupying a niche so precisely that competition becomes unnecessary. Each organism has a role, often subtle, often slow, but always important. The slope functions not because of any single star player, but because of countless small interactions happening quietly in the dark. The trench slopes remind us that life does not require comfort, only opportunity. Where conditions seem impossible, biology finds a way to adapt, not by fighting the environment, but by working with it. Pressure becomes a design constraint, darkness becomes irrelevant, and scarcity becomes manageable. These adaptations are not heroic in a dramatic sense, but they are extraordinary in their consistency and effectiveness. There is also humility in studying these places. The more we learn about the slopes, the clearer it becomes that our assumptions about habitability are narrow. Life does not need warm temperatures, abundant food, or gentle conditions. It needs stability, time, and the freedom to evolve solutions that make sense locally. The slopes of the Philippine Trench offer all three, wrapped in an environment that seems hostile only because we are not built for it. At the same time, these worlds are fragile. Their inhabitants are adapted to very specific conditions, and change does not come easily. Disturbances, whether natural or human-made, can have long-lasting effects. And understanding these ecosystems is not just an academic exercise. It is a step toward recognizing their value and the responsibility that comes with knowing they exist. As we pull back from the trench slopes in our imagination, what remains is not darkness, but complexity. A reminder that Earth still holds places where life operates on different rules, at different speeds, with different priorities. These places do not ask for our attention, but they deserve it. The slopes of the Philippine Trench are not the edge of life. They are proof of its persistence. Layered, resilient, and unapologetically strange, they show us that survival does not always look heroic. Sometimes it looks like waiting, adapting, and quietly thriving in conditions that would flatten a submarine sandwich without a second thought.